Yeah.
Hello, everyone. Sorry we're starting a little bit late. So welcome and thank you for joining us for our first Changing Planet seminar of the year. This session will be recorded. If you have any questions for either speaker, we will do them after both people have spoken. Please do feel free to use the chat. Please put your name and where you're from, just so we know. And it's my pleasure to welcome our speakers, Dr. Gbemi and Dr. Reshma, who are both newly appointed lecturers at the Grantham Institute. Today, they will be talking about the challenges of the scaling of hydrogen for clean energy uptake for a sustainable future. So first, I'd like to welcome Dr. Reshma.
Okay, thanks everyone. And I'm going to be talking, as always, asked to about hydrogen, but I'll be specifically also focusing on the materials challenges. So I'm partly based at Grantham, and should I just get rid of this?
Just maybe put it on your lapel or something.
Sorry. Okay, maybe that's better. Okay, so I'm partly based at the Grantham, and my home department is the Department of Materials. So I spend a lot of time trying to understand how materials function, and I'll go over the challenges as a materials scientist about green hydrogen. So looking at the global energy challenge, so that's really what motivates my work. Today we have 16 multiplied by 10 to a very large number of energy usage. And that's already a really large number, but if we look at 2050, for example, we're going to have at least 6 billion new energy users, right? And 3 billion of those are just a consequence of the population growth, and 3 billion of them are currently living in energy poverty, right? So if everyone needs to come up to speed with the energy consumption of the Western world, we need to then think about ways in which we can at least multiply our energy usage by a factor of 4. And we don't need to do, ideally, we don't need to do that using fossil fuels, but we want to replace this picture on the left here, where we are currently burning a huge amount of fossil fuels and producing a lot of CO or NO, for example, with a picture that looks more like this, right? So it's a much more circular picture where you're taking renewable energy and using that to convert molecules. For example, what we'll be talking about today is using renewable energy to convert water into hydrogen, which can then be used either as a fuel for fuel cells, for example, but it can also be used to power things like heavy industry. And essentially, when you burn or combust hydrogen or use hydrogen in these different technologies, you essentially get back water as your only byproduct, right? So unlike these cycles on the left that emit CO or CO2, on the right you have much more of the circular picture. Obviously, the challenge here is if we think about renewable energy and water is a very stable molecule, right? It exists very happily on our planet. So if we really want to split that into forming hydrogen, we need to think about catalysts that can accelerate or drive this reaction, right? And that's a critical bottleneck that I'll be focusing on today, thinking about technologies that can take water and then split that using renewable electricity into hydrogen. So why hydrogen? I think both Gbemi and I are obviously very passionate about this, but just taking like a bigger picture overview, why hydrogen is perhaps an interesting fuel to produce. So obviously you can put it in a fuel cell car. That there are already light vehicles that can take hydrogen in a fuel cell kind of configuration for a car. But we're also thinking about heavy duty transport, right? So thinking about bigger trucks, bigger buses, railways, what happens to things like shipping. So looking at the right here, either hydrogen directly as a fuel for shipping, or using hydrogen and converting that with a carbon source for making things like low carbon jet fuels, right? And currently a lot of our hydrogen is produced using steam methane reformation, and that ends up producing a lot of toxic CO gases. So if we can produce it using solar, wind energy, and water, that's obviously a very nice way of producing this fuel at scale. We can also think about other industries. So a lot of people don't really focus on the heavy duty industry. So this is things like steel production, cement production, things like methanol manufacturing. So these are where a lot of our chemicals come from, and currently we use a lot of carbon in there. So for example, for steel manufacturing, you might start with a metal ore that you need to reduce to a metal, and what you use there is essentially coke or carbon as the reducing agent. So looking at hydrogen as replacing the carbon source, there's another kind of really interesting area. And then the other one is the Haber-Bosch process. I think some of you might be aware, but in the 1900s, this was one of the famous inventions that is being able to sustain the planet as we know today, and being able to sustain the huge amount of population. So this essentially produces fertilizers, so ammonia, which allows us to grow crops at the scale that we need to feed the growing population. But it's also one of the biggest CO2 emitters, right? Because essentially this process is high temperature. You need nitrogen and hydrogen to react at high temperatures. The hydrogen is produced, again, using steam methane reformation, and it's a hugely emitting process, right? So if we can get the hydrogen input into that process with green energy, that helps us save a lot of CO2 emissions there. So I've been talking about different ways in which hydrogen is currently produced, and if we take a step back, we can look at all of these different colors of hydrogen, and these are only 4. I guess if you pick up any newspaper these days, I saw a white hydrogen this morning. So there's all sorts of different colors, and people like to brand different colors of hydrogen to make it look as if they're actually making progress in this area. But where we started with was brown hydrogen, which is extracted from coal using gasification. Gray hydrogen from natural gas. This is using steam methane reformation, produces a huge amount of greenhouse gases. It's predominantly the way we produce most of our hydrogen today. We want to go to green hydrogen, which is completely renewable in the sense that it takes renewable electricity and couples that with water electrolysis and uses that to produce directly hydrogen. There's a huge push from specific currently polluting industries to have this intermediate step of blue hydrogen, where essentially is still producing hydrogen using fossil fuels, but you have this element of carbon capture. So there's people who then think, well, if green hydrogen is too difficult, let's have a blue hydrogen step along the route. And there's a huge amount of debate whether this is a sensible way to go, or whether we should really be pushing technologies to go all the way to green hydrogen. And in the UK particularly, in 2021, in August or so, it had the UK had proposed their hydrogen ambitions and their hydrogen goals, and it's interesting to see where the UK thinks we're going. So we look at the terawatt hours of hydrogen production, and it's around 27 terawatt hours today, right? And most of that is, again, steam methane reformation. So nothing, a very, very small fraction of that is actually produced using green hydrogen. And because of hydrogen's application in all of these different industries and powering heavy duty transport and a lot of these different chemical sectors, we want to increase that production by at least 10 times, right? And we not only want to increase hydrogen production by 10 times, but by 2050, we would ideally like most of that to be green, right? So the numbers and the ambition to where we want to get to is quite massive if you think about it just from a scientific standpoint. So how do we do that? If we want to think about green hydrogen, there's several different competing technologies. So left to right is going to be the one that's most developed, going all the way to the more nascent technology. So this is the way hydrogen's been produced for decades, right? Green hydrogen's been produced for decades. And if you've done any kind of electrolysis in school, this is the experiment that they show you, right? You have a massive tank of electrolyte, you dump 2 conducting electrodes in it. One electrode evolves hydrogen, the other evolves oxygen, right? There's challenges with this, particularly you can't get very high rates of hydrogen. And if you imagine you have a massive tank of electrolyte, that's not going to be very quick to turn on and turn off. And particularly when you're coupling with things like renewable electricity, you want things to have a much faster time response. And having a massive tank of electrolyte is probably not the most efficient way of thinking about this. So there's proton exchange membrane electrolytes, where essentially proton exchange membrane water electrolysers, where essentially we replace this massive tank of electrolyte with a conducting membrane, right? So now you have a very compact kind of device, and you can stack multiple of these together to get higher amounts of hydrogen production. There's challenges with proton exchange membrane that I'll be getting to, particularly the catalysts that we use are based on really, really expensive metals. So while this technology works, and the hydrogen strategy of the UK singled out this technology as probably one of the most promising ones that we should focus on, there's also a push on, well, so this works in acidic pH, and that makes the materials challenge really, really hard, because we need to find materials that can essentially operate in extremely acidic conditions, which is challenging. And we say, well, what about alkaline conditions? Can we get a broader set of materials that might operate? So people are now starting to look at these alkaline exchange membrane electrolysers. And then the final, these are the four main technologies. There's a lot of other technologies out there, but the final one that I'm going to look at today is the solid oxide electrolyzer, where this works at high temperatures. So you essentially get rid of the membrane, and what you have here is essentially a solid oxide conductor, right? So you're conducting oxygen ions through a solid. And it has good efficiencies, the system, but it needs to operate at 700, 800 degrees. So a lot of people working on these technologies are thinking of ways in which you can reduce that operating temperature. So these are the two primary technologies. There's alkaline water electrolyzers. So this is the conventional electrolyzer where you're dipping two electrodes into a massive tank. And then there's the PEM electrolyzer. So you can see, I guess the good things here is if you look at the PEM electrolyzer, we're drawing significantly larger amounts of current density, right? So this is probably a promising technology that we should work on. So here you can see it's about 0.4. We get an order of magnitude higher currents when we're looking at this specific configuration. But in a slightly less ideal situation with these technologies, you can see thermodynamically, or if you had an efficiency of 100%, you would need about 1.2 volts to run these electrolyzers, right? And this is data that's more practical from real devices, and very quickly we can see, for example, even for a PEM electrolyzer, to get about the 6 amps, you're applying probably 2 volts, right? So that's really chewing up into the efficiency of the system, right? So quite far away from really operating at this thermodynamically 1.2 volt number, right? So you can look at where the breakdown happens for this kind of setup, and you can see a large fraction of this essentially happens at the electrode where you are splitting water to form oxygen, right? So while the hydrogen bit is the one that you really want to produce, it's really this reaction that needs to happen at the other electrode that's limiting your overall performance, right? So as a material scientist, I spend a lot of time looking at catalysts that we can develop to really accelerate the rate of this reaction. So if we can get this green bit all the way down as close as we can to this blue line, that's where we want to be. And finding materials that can help us do that might significantly reduce the actual voltages that we need to apply to drive this reaction. And we don't need to look far for materials that do this really well. So the oxygen evolving complex, so this is how plants will produce oxygen, right? It relies on a similar reaction. It takes water, it takes sunlight, it splits the water to form oxygen, and then you can convert the hydrogen bit with CO2 to essentially form carbohydrates and things that plants can use, right? So doesn't matter what the actual structure looks like, but that's where the efficiency of a plant, the enzyme in the plant doing the reaction is, right? So you can see it's about 1,000, the rate of reaction is 1,000 oxygen molecules per second, right? And these are some of our best catalysts that we can make, right? You can see they're about 0.1, at best 1 oxygen molecules per second. So 3 orders of magnitude between the best catalysts that humans can make and the ones that nature has designed, right? So we're trying to understand how does this work how do these, what's so special about this structure, and can we mimic that using some of the technologies that we have available in the lab. Oops, that went quickly. Sorry. So looking at the proton exchange membrane electrolyzer, so you have the oxygen producing electrode, the hydrogen producing electrode, and I've said the oxygen part is the real bottleneck, and you can see you have a thick catalyst layer here, right? And the real issue is not just you need a thick amount of catalyst, but one of the only materials that can successfully catalyze this reaction is based on iridium. And iridium is a huge problem, because if we look at a graph like this, where you have the price versus the annual production, you can see iridium is probably at the worst place possible, right? So we don't produce a lot of it. It's extremely expensive. And if we want to scale up this technology to terawatts and have entire economies depend on it, you probably don't want to do that based on a material that's so less abundantly available, right? And an exciting or one interesting aspect of iridium, it's a byproduct of platinum mining. So we mine for platinum, which is already a really rare element. And then maybe in a platinum ore, you find some amount of iridium, right? So its supply is not even really well controlled. So a huge challenge for us is trying to understand what makes iridium work as a catalyst for this reaction, and can we then think of ways in which we can reduce or completely replace iridium as a catalyst. And so there's a lot of road mapping by the Royce Institute, which is the UK's materials kind of consortium of different academics. And they suggest that we need at least a 25 to 40-fold reduction in iridium if we need to make these technologies viable at the terawatt scale. So what do we do about it? So there's, well, if we need to go away from iridium, and you look at the periodic table very quickly, you see there's a huge possibility of materials that you can bring together as possible candidates, right? But it's really, really hard to know which one of them will work as a catalyst. So we try and understand what really happens at a catalytic interface. Can we really understand how iridium functions as a catalyst for this reaction? And then can we try and mimic some of its properties in a more abundant material? So we look at the atomic scale, we look at the sub-second time resolution to try and understand how these reactions happen at a more fundamental level. And we look at all sorts of things. We see how the catalyst evolves, we see how the water evolves. We try and, so there's a huge potential gradient as we apply. So this is a couple of angstroms, right? So really, really tiny length scales. You're applying a huge potential gradient across that. And it's really interesting to see the dynamics of how the electrode evolves, how the electrolyte evolves. We spend a lot of time trying to understand that degree of complexity. So the next few slides, not going to go into the science a huge amount. I just wanted to show 5 really quick examples of the kind of things we do. I don't expect you to understand or take away all of this, but just to give you a flavor of the kind of science that we're looking at. So this is how an iridium catalyst would look like. We've spent 4 or 5 years now trying to figure out exactly what this interface looks like at a molecular scale, right? So we go to massive radiation facilities, put our catalyst in some of these radiation facilities, try and understand, well, what are these critical bonds that form under reaction conditions? What is this bond length? What's the oxidation state of iridium? What's the really active site for this reaction? We also spend a lot of time looking at what the interfacial water looks like. So when water is present at a really polarized interface, it doesn't have a similar structure to the water that you might have in a glass, right? So it has a very specialized structure which determines how easy it is to split into hydrogen and oxygen. So we spend a huge amount of time trying to understand these interfaces and then trying to mimic how something like manganese, for example, that's much more abundant, how that would function as a catalyst. We also look at, so this is now, while this was very kind of atomic scale and really looking at the atom by atom picture and trying to see where this reaction happens, we can also take a step back and look at an entire device, and we do this in collaboration with industrial partners, for example, Johnson Matthey, who makes like a little device for us, and we start to then see how does this material evolve when it's placed in an actual device. It's quite interesting. Some things are quite similar, but as soon as you start putting things in a device, there's a lot of different interfaces that you can access, and things start getting very complex. And as a material scientist, you can then start to see why this problem of shaving off iridium is really, really challenging for us. The other thing that we try to do So currently we don't have a material that can support iridium, right? So some people might say, well, you can have really tiny clusters of iridium and just put it on a catalyst support, right? So that's one way of shaving off a huge amount of iridium, just use a material to support catalysts, right? And this is what people have done and to make fuel cells viable, for example. So Toyota Mirai, that essentially works on having a platinum catalyst, and they're very good at having these carbon supports, so carbon really abundantly available, and they put these tiny atomic clusters of platinum. It doesn't really work quite well for us because we're at such oxidizing conditions that pretty much all materials in the periodic table just oxidize and passivate under these conditions, right? So what we're doing in current commercial water electrolyzers is putting down a massive chunk of iridium as a support for an iridium catalyst, right? And that's because we have nothing else that can replace this support, right? And that's a huge waste of a really precious element. So we're looking in collaboration with Tier Coatings, which is essentially a coatings company. They do coatings for all sorts of funky applications, but we're working with them to see, can we replace this catalyst support with materials like titanium or tantalum, which might be a bit more abundant. And you can see quite quickly here that these current densities are very far away from the 6 amps that I'd been talking about a few slides earlier, right? So we've suddenly gone to milliamps when you're looking at these materials, and in a few hours of operation, titanium will just form titanium oxide, which doesn't conduct electrons anymore, right? So it doesn't really work as a support for this technology. So that's a huge area of interest for material scientists and things where a lot of active research is ongoing, but no grand solutions to date, unfortunately, but a lot of work in progress. So something that I'm also very passionate about is if you look at a whole electrolyzer setup, you can see the electrolyzer is only a tiny bit of the entire system, and a main portion of the system is taking water, purifying it, then going through all of these ion exchange membranes to make the water really, really pure. So the water that actually is fed into electrolyzers is pure to parts per trillion, right? So extremely pure water feeds. But when you look at the kind of water that's most widely available to us, it's 97% of our water resource or so is present as seawater, right? So again, if you want to scale up these technologies to the terawatt level, going through so many levels of purification is probably not going to be viable at scale, right? So a lot of my work currently also looks at, well, can we think about what happens at these interfaces? All I've been talking about right now is just taking water molecule, splitting it into hydrogen and oxygen, right? But the minute we start taking things like seawater, wastewater, you have all of these different components in the water, right? And a particularly problematic one, if you look at seawater, is chloride ions, right? So sodium chloride, abundant salt, abundantly present in seawater, a huge challenge for us because it essentially is very happy to be converted to chlorine gas, and producing huge amounts of chlorine gas in electrolyzers. It's definitely not good news for the catalyst stability, but you probably don't want devices that are producing a huge amount of chlorine gas, right? So technologically, the activity gets a lot worse when you start looking at even, you don't even need to go to seawater, right? Even tap water or drinking water, the activity is a lot worse. Selectivity, instead of oxygen, you're producing chlorine and all these different kinds of activating all of these different kinds of chlorine chemistry, which is a nightmare for us. And the stability then obviously takes a toll too, right? So electrolyzers, they were barely operating for hundreds of hours, and now in a couple of hours, they start to fail, right? So thinking about, well, can we somehow suppress all of these side reactions? How can we design materials that don't interact with chloride ions, right? And that's a huge challenge. And it's not all bad news. There's startups that are starting to evolve in the space, and people are starting to push this research from a lab scale to more kind of relevant setups, which is interesting. So a huge way to go for a lot of these technologies, but there's still scope, and people are doing a lot of interesting things in this area, which is always nice to see. So finally, I've hopefully told you that we produce hydrogen at the cathode. But what's really problematic for us is the anode. We need to apply huge potentials to drive this oxygen evolution reaction. More problematically, we rely on iridium, which we don't want to do. The reaction is sensitive to all sorts of contaminants, so we can't even go to things like seawater or wastewater. And there's a whole community of people saying, well, if water electrolysis is hard, why don't we just replace it with something that's easier, right? And one of the things that might be easier is taking things like hydrocarbons, or well, when I say hydrocarbons, it can be biomass waste, for example, right? So taking a waste source that has carbon and converting that to value-added products, right? And that instead of taking 2 volts, that essentially takes around 1.2 volts to drive this reaction, right? So in electricity, you're already shaving off half the cost of running this reaction, right? It doesn't rely on iridium, so you don't need, because you're not operating at 2 volts anymore, it's not as challenging a reaction condition. You can start looking at more abundant materials to drive this reaction. So that's a second advantage. And then thirdly, you're starting to then produce products that have really high value for things like the pharmaceutical sector, right? For things like the chemical production sector. And that's a really interesting, so when producing oxygen has all these sorts of challenges, right? And once we have oxygen, we essentially rent it out. So pretty much zero economic value. If we're now starting to sell the products that we are actually producing at the anode, we make it at a lower potential, so that's cutting down our electricity costs. The catalysts aren't as expensive. All of that ends up reducing the cost of green hydrogen significantly, right? And makes it extremely competitive, while also being able to decarbonize really challenging sectors like the chemical and the pharmaceutical sectors, which currently rely on a lot of different petrochemical feedstocks. So we look at different alternate reactions. So for example, biomass oxidation to dihydroxyacetone. It's a long name, but it's essentially a chemical that's used in the pharmaceutical sector. Actually, it's used for tanning, and there's a huge market for it. And clearly, people are ready to pay high value for it. So if you can produce green hydrogen while also helping the beauty industry, I think it's a way to reduce the cost of green hydrogen. And there's all sorts of interesting products you can make. So a lot of these are kind of can be used to make sustainable plastics. So don't worry too much about the big chemical names, but sustainable plastics and that sort of thing is what you can do with this. There's still challenges. So a lot of times you can't just take biomass and end up getting the product that you really want, and designing a catalyst that very selectively will just give you one of these products is hard. You don't make the products you want. Quite often you just oxidize everything all the way to CO2, which is another, creating problems rather than solving them. But we're working really hard in this space to kind of design catalysts that can very selectively give us some of these high value products. So with that, hopefully I haven't given you a lot of answers, unfortunately, but hopefully I've given you different kind of research areas and hopefully a broader perspective of how we think about hydrogen with the hat of a material scientist, and where the challenges lie in this sector. So that's a few key kind of takeaway messages. It's all very difficult reactions, and we really look at trying to understand how materials operate, how materials fail at all different length scales to help answer all of these different challenges. And then a lot of it is not me. We work with a lot of different people, so that's all of the people that I work with on a day-to-day kind of basis. But with that, I'd like to thank you for your attention and be happy to take questions.
I think taking questions at the end of both of you.
Awesome.
So I'm Gbemi. I used to be a lecturer at the Centre for Environmental Policy before I started my Grantham lectureship this year. We've heard from Reshma about the challenges with hydrogen production. My research major focuses on addressing kind of like the elephant in the room when it comes to clean technology uptake. Oh my God. Okay, do I need to start again? No? I'm still Gbemi. My name has not changed. So I kind of address the economics of it all. How do you make hydrogen cheaper? How do you create a demand pool? How do you quantify the impact of interventions in this space? And how do you create a tipping point? I'm sure we've heard about climate tipping points. There's also technology tipping points. People believe is the point where you've got sufficient demand to make the costs competitive. So to have cost parity with natural gas, for instance, or cost parity with grey hydrogen. I'm looking at green hydrogen anyway, or with blue hydrogen, or with coal, or with any fossil, but also the point at which you have cost parity with what it's used for. So if you have hydrogen used to make tans, for instance, and you have the incumbent technology, you want the cost to be the same. So that's the whole point of a tipping point, where you have sufficient demand to trigger that cost reduction and sustain it until you get to that point. And that's what we want to see for clean technologies, because transitioning to a sustainable future is not trivial. Now, when that point happens is unknown for clean technologies, because as you will imagine, it's technology specific, it's end use specific, it's country specific as well. But we know it happens along this innovation or this diffusion pathway of clean technologies. So that's what I'll be unpacking for hydrogen and some of the work I've done in this area. Now, the challenge is hydrogen at scale is stuck here. There are numerous demonstration plans on how to make green hydrogen for industry, green hydrogen to make e-fuels for aviation, but there is really no supported commercialization, and that's because there is no demand pool for hydrogen. No one is buying green hydrogen. Although there is really no supply, I think green hydrogen is still less than 2% of the global hydrogen market. But a lot of people believe that for key energy vectors like hydrogen, a demand pool will drive the market. People wanting to buy hydrogen will drive the market. However, the cost is very high. And there is a lot of supply push, so there's a lot of research and development going on to improve the performance of electrolysers, but there is no demand pool. Now, the advantage of a supply push like an R&D to make it better is what we call the learning by innovation, which contributes to cost reduction. The advantage of having the demand pool is like learning by doing, an economies of scale, which also contributes to cost reduction. But the greatest contribution or contributor to cost reduction is using and building bigger plants. That's where you have the biggest cost. So I always ask myself the question in my research: how do you generate sufficient demand pool and sustain it to bring down the cost of hydrogen? And this is where the end use case is important. Now, Reshma alluded to it. One of the best end use cases for hydrogen where you get that sufficient demand is from industry. So from heavy duty, energy intensive industries like iron and steel, chemicals and petrochemicals, cement, shipping, using hydrogen to make green ammonia, blue ammonia, e-methanol, as well as aviation. And there are different types of technologies to decarbonize these sectors, but hydrogen is key, whether green or blue or pink. Now, for these end use cases that can generate that demand pool, how do we design interventions to reduce the cost so we can generate and exploit that demand pool to trigger for that cost reduction until you get to the tipping point, if it does exist? Now, the role of interventions cannot be overstressed. You will need interventions to arrive at this tipping point. Now, we understand that the cost of hydrogen will reduce with time as demand increases, and there'll be a point where that cost will be kind of equal to the business as usual, or there'll be some form of cost parity. Now, an intervention could be non-incremental, where we put pressures on government to promise or release market-based policy instruments that pay for the difference between hydrogen and natural gas, for instance. Or you could have incremental interventions where you just design the intervention to generate that demand pool that you need to trigger for that cost reduction according to the learning logic. Now, interventions can be designed in different ways, and they're plethora. There are different types of interventions today, from consumption, gas consumption taxes, to emission trading schemes, to carbon abatement incentives. My research has shown that you need both external interventions related to market-based policy support, and also internal interventions related to what you can do within the production facility or within the end-use system to bring down the cost. So I'll explore these two areas today. Now, my approach, my core expertise is the development of participatory optimization framework to answer these questions. How do you get to the tipping point with hydrogen? How do you design interventions? And I don't just look at hydrogen, I look at carbon capture and storage. I look at production of e-fuel. So how do you design interventions to get to that tipping point? How do you explore external and internal interventions under uncertainty? So the key role is kind of like to have this clean innovation system, the existing market-based policies all over the world. I take a global perspective to my modeling, as well as participatory elements, looking at each end-use sector, what's their willingness to pay, as well as what is the possible learning curve from technology manufacturers. And then we throw it into a box, an optimization model, to generate some key outputs that will look at the total mitigation costs associated with the option, as well as the endogenous tipping points and the exogenous tipping points. And the key part of my work is handling uncertainties, because there are lots of uncertainties in hydrogen manufacturing, in hydrogen use, and we do that through like a solution space that combines different optimization frameworks. So that's like the core part of my research. But going to the fun bits on how do you identify hydrogen tipping points? Can we get to these tipping points? I'll look at two applications. I'll look at an internal intervention where we can exploit waste heat from electrolysers to drive down the cost of hydrogen, and an external intervention really assessing the UK's hydrogen policy today to see if we have sufficient or if we have robust policies to get us to that point where we can generate sufficient demand pool for hydrogen. Okay, take a bit of time. So something about electrolysers is they're not efficient. So there's a bit of waste heat generated. The heat losses reduce as they become more efficient. And one way to reduce the cost of hydrogen, as Reshma said, is to exploit these byproducts, whether they are stuff for tanning or actually on the energy side. So we apply the model to see if we exploit the waste heat from electrolysers, do we get sufficient revenue to reduce the cost of hydrogen as an internal intervention. Now, if you're thinking of how to reduce the cost of green hydrogen, for instance, the first thing will be, can we reduce the capex of the electrolyzer? Can we reduce the uptakes? Is there some grant funding for this? And no matter what you do to reduce the capex or the uptakes, even offering a discount rate as low as 3%, the reduction in the price of green hydrogen is very low. It's almost like a noise compared to blue hydrogen or even compared to natural gas. So that's why we have to look at internal interventions more in a clever way, such as how do you exploit the byproducts. If you look at the byproducts from hydrogen, which is the waste heat here, that's the green bars here. If you can exploit the waste heat, you can reduce the cost of hydrogen, but also if you then exploit waste heat from if you use curtailed winds to make hydrogen, and exploit the waste heat from that process, you can get to a negative price of hydrogen, subject to uncertainties, of course, as well as some form of co-ownership mechanisms with wind farms to make hydrogen. So in some sense, it's better to explore the byproducts as an internal intervention to drive down the cost of hydrogen than funding a capex or releasing grants to fund the capex. The second case I'll look at today is UK's hydrogen policy and if it's sufficient to get us to a tipping point. So there are 3 policies the government is pushing for hydrogen. So there is the Industrial Hydrogen Accelerator Programme, which is a grant to give £26 million by 2050. And then we'll have the UK's emission trading scheme for hydrogen, as well as the low carbon hydrogen business model, which is to pay for the difference between hydrogen and natural gas, for instance. Now, here we're looking at the previous study on the reduction in the price of hydrogen due to these internal interventions. One thing we picked up from that is producing hydrogen from curtailed energy. For instance, now if you produce hydrogen from curtailed energy, so instead of curtailing wind, you use that wind to produce hydrogen, the price of hydrogen reduces. Now, what we've seen as a national study is in the UK, there is sufficient energy from curtailed wind to make hydrogen, to make it more cost competitive, but it's not sufficient to satisfy 100% of the demand for the end use sectors we're considering. So energy intensive industry, heavy duty transport like shipping and aviation, but it has potential to reduce the cost of hydrogen. So if we look at the 3 policies, so the Industrial Hydrogen Accelerator Programme, as well as a combination of the hydrogen business model and the ETS. In the first case, by just producing hydrogen from curtailed wind, it's possible to have some form of cost parity. So the green is green hydrogen that is produced from dedicated offshore wind. The gray is gray hydrogen, and that's blue hydrogen. So without policy support, if we just follow the Lenin logic for hydrogen, it's possible to have cost parity with green hydrogen from dedicated wind, as well as to have cost parity with blue hydrogen from about 2044. That's when we expect a tipping point to occur without any policy support. And for grey hydrogen, well, a tipping point probably not occur. So probably need some legislation or mandates to stop that. Now, 2045 is too far to have a tipping point if we are to get to net zero by 2050, because basically the market will not move until you have a tipping point in the technology. If you look at the Industrial Hydrogen Accelerator Programme, which is a grant scheme, a tipping point doesn't occur until the same time period, 2024, 2025, because this is simply a grant, the CAPEX grant, for instance, which if you look at the detailed study, it makes no difference. But if you combine the hydrogen business and the ETS, the reason why we're combining both is you can use the income from the ETS to support the hydrogen business model, because currently in the UK, the proposal is to support the hydrogen business model by taxing end users. And we're saying you just need to use the income from the ETS. If you do that, then you can have cost parity from the 2025, in 2 years' time, if the government is committed or they remain committed to the hydrogen business model as well as the UK ETS. So in some form, you want to use like a mix of policy support, especially these external interventions, to support the tipping point, and that's what just shows, as well as the cost of each of these interventions. The second case, the third case I use the model to assess is the 10-point plan. by the former Prime Minister, which is still bankable, I think. In that plan, there's a promise of 5 gigawatts of low carbon hydrogen by 2030. Now, that's equivalent to about 16 terawatt hour of hydrogen. And there's always a question of, is 5 gigawatts sufficient? Is it sufficient to get us to a tipping point, for instance? And so this is like the price region for hydrogen. And this is like the price region for natural gas. And you'll see the government did think about it. 5 gigawatts is the point where hydrogen becomes competitive with natural gas. But there are two things here. This low price of natural gas is the price of natural gas before the war, before the Russian-Ukraine war. And this bottom line is the most optimistic projections for hydrogen cost reduction. So the government is playing safe by promising 5 gigawatts. I mean, so should the government promise 10 gigawatt, 50 gigawatt, 200 gigawatt? At what point will a supply push of this kind create a tipping point? And what we say that it will never happen if you only rely on the supply push. So even if the government promises 50 gigawatt or 500 gigawatt, it will just not get to a tipping point because the price of hydrogen will continue to vary as well as the price of natural gas. So what's the best solution? A balance of the supply push policy as well as the demand pull policy. So in this case, keep the 5 gigawatts as it is, make no more promises, but play around with your demand pull instrument like a subsidy, a hydrogen subsidy, as well as a tax pulling from the ETS. At that point, we'll get to that tipping point for hydrogen. So I think that's a summary of everything I was going to talk about, really quantifying the role of policy interventions in getting to tipping point for clean innovations. Thank you.
Thank you both so much for your talks. We'll now take questions from the room and maybe some from online if we have time. Do we want to start from anyone in the room? Any questions? Oh, John.
Can I just ask about the first talk question first?
Could you take the mic? I was going to take the microphone too.
Oh, okay. Oh.
Sorry.
Oh, sorry. Yeah, I know most of the things we're talking about, the issue of the material supply. And I know you mentioned, I have two questions, that's right. First, you mentioned about manganese, and I was thinking that's used a lot in the battery industry. And how would that compete with each other, looking at these two industries, if they do decide to both use it? And then secondly, I was wondering, talking a lot about the resource issue, but also what's the issue of like the chemical synthesis of these new ideas and how much energy is required in chemicals, and is just the actual pathway of making these catalysts a lot more possibly complicated and a bit more dodgy potentially?
Yeah, I guess both really interesting questions. So the first one, manganese is more abundant, so potentially there's scope for both batteries and electrolysis to use manganese, especially considering there's a lot more push for material recycling, at least in the battery sector. So hopefully that'll, fingers crossed, become a more closed loop materials where they're using and recycling materials. But yeah, I think there's in terms of abundance, I think it's possible for both sectors to use manganese. That should be fine. And the second one was, how do we process these materials at a larger scale, which is also interesting. So for a lot of these new materials that we're developing, we work closely with industry who's has a bit more insight on how to do this at scale and quite cheaply and not be energy intensive in those processes. But there are materials that are coming out now which are quite exotic, and people do it with all sorts of different techniques, which I think is just more of a proof of concept of you can make X materials. But there's a lot of techno-economic analysis of, when you think about scaling up, is this a possibility, and is it worth taking to the next stage of commercialization, which is a super important point to think about. and there's a lot of buzz at the moment about designing materials for the end use when you start. So not even wasting too much resources in materials that might potentially be good, but they can't be synthesized at scale.
Any questions from online?
No, but I've got a question.
Okay.
Question for Gbemi. What do you think is the chance that the UK government won't stick to its plans on hydrogen and its plans to stay in the EU ETS? And where should we be applying pressure if we want to make sure they do?
Thank you. I mean, the UK is already developing the UK ETS, so that's moving away from the EU ETS. The challenge with most governments is how to reduce or how to use the little they have to go a big way when it comes to designing policies for clean technologies. And I think this is a global problem because most times we say the cost of the transition is X trillion dollars, or it will cost the UK X billion dollars to transition to net zero. And we kind of expect the government to just give that X trillion dollars, forgetting that there are different competitions for that money in terms of other users. So I think the challenge is creating a tool or helping them to consistently invest in clean technologies, because that's what we need to get to the tipping point, really that incremental intervention, as opposed to not doing anything or doing too little, but just doing the optimal. Now, I don't know, I can speak for the current government. They seem to be going up and down with these things, to be honest. But it's really about, but historically, I'm not surprised, because historically, every time we got to a point where energy became too expensive, fossil fuel, I thought that would be an opportunity to move away from fossil fuel, but it's never happened, even in the 70s, because we are thinking about cost instead of value. So I think if governments continue to think about cost, they wouldn't make the right decisions. We need to start thinking about value to the economy, value to the ecosystem.
Any other questions for you?
Yeah, this is to either of you basically, but Reshma, you mentioned about blue hydrogen and how some people are using this or some industries using it as a stepping stone. And do you think this is a good idea, or do you think that the money and investment should be put straight into green hydrogen and accelerate that quicker, or do you think it's good to have it as a stepping stone if it's too slow?
I guess this is more of a very personal opinion.
Yeah.
But I think if blue hydrogen is currently existing in certain industrial sectors, that's fine as a stepping stone, but investing a huge amount of research money in developing technologies for blue hydrogen for 2030, 2035, I'm not sure I completely agree with that, because that's essentially saying in 2035, 2040, the technologies that will be deployed still basically use fossil fuel. I think if industry currently is using carbon capture, that's fine as a stepping stone. But I don't know, Gbemi probably knows the maths and the numbers better.
It depends on the end use case. So if you're looking at the industrial sector, there's a good case for blue hydrogen, because blue hydrogen enables green hydrogen. Now, the investment in blue hydrogen is not as high as the investment in green hydrogen, because blue hydrogen is produced from technologies that already exist. So for specific end use cases where it's difficult to find alternatives, making blue hydrogen for those end use cases, are because of the volume of blue hydrogen, it will have a ripple effect over the price to reduce the cost of green hydrogen. I wouldn't recommend blue hydrogen for homes, no, but for these end use cases, yeah. So most times we say blue enables green. If it's cheaper to have a green hydrogen future if you use blue hydrogen for these cases than invest in green hydrogen for these end use cases that will create a demand pool.
Thank you.
I just want to get some clarity on whether or not you think nuclear produced hydrogen is green or blue.
It's pink, isn't it?
It's
Sorry.
How about
Hydrogen
that?
produced using everything is called a different
If we
color.
consider the previous question, where does that fit into your second generation?
I know to my mind, pink is more towards green than blue, right? That's how they see it in the scales. So they still think it's kind of produced via renewables, but not all the way with solar or wind. But yeah, it currently has its own color because they can't figure out, I guess, exactly where it should sit.
Hi, thank you for excellent talks. I just have a question for Gbemi, is it? Yeah. So without the UK ETS, what would be the next best policy toolbox or a set of interventions that will allow us to get to the tipping point, at least in the midterm, yeah. In your opinion, anyway. Yeah.
So there's no unicorn when it there's no unicorn when it comes to policy support. So my research has shown you always need a mix of incentives and disincentives. So you need to tax as well as subsidize to get to that tipping point quicker. But the key is the timeline for these policies. So we follow the social technical diffusion theories. You've got these innovators, so people today who will buy green hydrogen and use green hydrogen irrespective of the cost, and that's like 5 to 10%. And then you have the laggards, people who take their time. So it's really using this mix of policy support to do that. Now, what we need now are gap fillers. So it's a global market for hydrogen. The US is doing their own thing, the IRA, the UK is doing their own thing. It's actually been able to simulate these impacts on a global scale and see where we need to fill the gap to get to the tipping point for blue hydrogen, or for hydrogen, green hydrogen, which is my preference, either on a utility level, on the energy vector level, or on the end use level.
Okay, that is all the time we have for questions, unfortunately. Let's give a round of applause to our speakers.